Hi everyone, today we're going to talk about market price prediction. The objective of this project is to develop a robust time series machine learning model that can accurately forecast in market trends based on historical data. So we're gonna have a planning that contains data pre-processing, exploratory data analysis, feature engineering, model selection and training, model evaluation and fine-tuning and validation. And finally, we're gonna have a conclusion. Before we start data pre-processing, we're gonna have a look about our dataset. Our dataset contains the market of the commodity under consideration, the month for which data is recorded, the year corresponding to the recorded data, the quantity traded, the minimum price of the market, the maximum price, the mode price, the state, the city, and the specific date of the recorded data. So let's begin our data pre-processing. As we know, data pre-processing is a very important step in data mining and data analysis in general to make raw data and transform it to a format that can be understood and analyzed by computers and machine learning. So in our case, first of all, we're gonna start about data cleaning. We will found we will look for non values, duplicated values, etc. And then we have to convert date to a date time variable. In the end of this step, we found that there is non-null values and we have clean data, and also we converted the date variable successfully. To identify trends, seasonality, and anomalies, we should use exploratory data analysis, or we call it EDA. In this step, we're gonna visualize the model price and the time over the time. So we found that the model price increased over the time. Even though we looked at there is a little bit of noise in this visualization, we're gonna fix that by feature engineering. To improve model performance, we're gonna create relevant features. As we know, feature engineering is the process of transforming raw data into relevant information for use by machine learning models. So in our case, we're going to create leged variables, role-in statistics, variables, and seasonal indicators. There is an example of the code. We have data of price mode lage 1. We create a new column that's called price mode lage 1 that equals data price mode point shifts 1. We do the same for roll-in statistics. We took the roll-in, the average of the roll-in, and with the window equal to 3. We do multiple variables for each one. Now we're gonna move to model selection and training. For model evaluated, we're gonna choose ARIMA, SARIMA, and LSTM. So what is ARIMA model? ARIMA model is an acronym for autoregressive integrated moving average. Autoregressive is the equation terms created based on past data. Integrated is accounting for overall trends in the data. Moving average is the equation terms of error or noise based on past data. For the performance, we're going to use MEO, MSO, or MSO. Seasonal arima or serima, the part of autoregressive is the same as non-seasonal arima. The moving average part accounts for the influence of past error terms in the current value. The integrated part indicate the degree of differency applies to the data. Seasonal components. Sarima introduced seasonal components to account for patterns that repeat over specific time intervals, like daily, monthly, yearly. So the components include seasonal autoregressive terms donated by P. They capture for relationship between the current value and the past value at seasonal legs. Seasonal moving average donated by Q. They account for the influence of past error terms at seasonal legs. Seasonal differentiation donated by D. It represents the degree of seasonal in each season. For example, 12 for monthly data. In this slide, we see also the difference values of the mean error, MSO, and RMSO. Finally, we're gonna use a type of recurrent neural network architecture widely used in deep learning. It's LSTM, that is an acronym of long short-term memory. Here is an example of the code and also the values of the performance and difference metrics evaluation. For model evaluation, we're going to use evaluation metrics such as mean absolute error, mean squared error, and root mean squared error. To compare between models, we're going to look at the comparison table. So we found out that LSTM has the best performance among the three models as it has the lowest mean absolute error, mean squared error, and root mean squared error. To improve model performance and validate on unseen data, we're going to use fine-tuning and validation. To use that, we're going to have we have to adjust model parameters, validate on separate validation sets, and iterate as necessary. Here is an example of code here. To conclude, we successfully built and evaluated multiple time series model, compared models using key performance metrics, and fine-tuned models to improve accuracy. And bye! Thanks for watching!